So it was an interesting session. So we have heard a lot about waves, not much about eddy. So it's more about eddy flavor, mesoscale eddy flavor in the background. So I'm interested in understanding the Lorenz energy cycle. So it's a classical diagnostics to estimate how the ocean is forced and dissipated, understanding the different kind of conversions that goes into the system. So typically, what we do in this, so initially mentioned it before, so we have a description where we split two types of reservoirs. We have a kinetic energy and available potential energy. And we split each reservoir into a mean and AD. So we have mean APE, mean kinetic energy, and AD APE, kinetic energy on each. So you have buoyancy fluxes creating mean potential energy as well as AD potential energy. Then everything can be dissipated and we have conversion. The kinetic energy, the split is the classical EWM decomposition into mean and rotating components. So the classical description is based on approximation, where the mean AP is in terms of this is a horizontally averaged density field. So somehow the AP is described as a sort of a risk scale density variance. The mean defined relative to the horizontal mean density field, or the AD relative to the fluctuating part relative to the mean. So it's important to generally it's important to we believe that it's in the atmosphere and the ocean is kind of dominated by instability. So there is a conversion between mean APE into AD APEs and into turbulent kinetic energy. So it's kind of believed to be associated with one of the key conversion in the ocean relative to the giant Maclaurin parametrizations. So what you can do is also look at the Lorenz energy cycle as a way to look at energetically consistent models, where you say that you, instead of being between mean and AD, you look at the problem as a decomposition between a resolved energy reservoirs and a subgrid-scale energy reservoir. On energetically consistent models, you want to have a description of the subgrid-scale energy reservoir. So you have your turbulent unresolved kinetic energy, unresolved potential energy. So the giant Maclaurin, the mesoscale parameterization, you can show that it kind of converts a mean AP into AD AP, but it's immediately converted into turbulent kinetic energy. So the giant Maclaurin parameterization kind of acts this way, converting directly a mean AP into turbulent kinetic energy. And you have isopycnal mixing, constant rotated diffusion, that tends to be associated with these red arrows, where you convert which are the two conversions are basically a source for AD or unresolved AP, and at the end of this dissipation is what's called mixing. So the mixing that we are all interested to link to the sources of stirring, whether climate change can affect this is kind of related to this the budget of AD AP, in my view. So we have a synthetic description of ocean energy cycles that we can either use to diagnose the energetic ocean models, or use as a basis for thinking about energetically consistent parameterization. So in practice, it's always been used in terms of this called Lorenz approximation, but an exact theory of AP has existed for over 50 years, was developed in 1981. But as far as I know, nobody used exact theory. Still, 15 years later, using the same called Lorenz-Kinsey approximation. So there have been some attempts by Stewart et al. In kind of angular geometry to evaluate Lorenz-Kinsey approximation, and which they show that in some places it can be 100% inaccurate. So here the goal is to kind of first use this a little bit more and try to understand more what's going on, evaluate this approximation in terms of what are the implications for estimate of buoyancy power input, the conversion, on the budget of ADFE, among other things. So a little bit of history. So what we use originally is Lorenz theory defines APE as a global construct, defined as a difference between the potential energy of the system minus the potential energy of a state of minimum potential energy obtained by a adiabatic arrangement. So it's only valid as a global construct because if you write it as a volume of the difference of potential energy, variable parcel minus reference potential energy, this term is really positive or negative. It doesn't really have any physical meaning in terms of forces involved in making up of available potential energy. So what Andrews and Holiday and Remi Tailleux did in 81, they show that you can in fact construct a theory from a local principle. And they find that the limit, you can write the APE as a volume integral of something that is non-negative, which is valid for finite amplitude perturbation, and it reduces the quadratic approximation is a well-known formula n squared, square the displacement square over 2. And basically the idea is that when you have a stable stratification, you move a free parcel up or down, you're always subject to restoring valency forces, and these forces are always working. You need always to produce work to move a parcel from a reference equilibrium in a stably stratified fluid. So it's kind of more physical because now the local APE represents the work needed to move a parcel from a resting position. But the original framework was quite complicated. It looks simple like that, but if you read the paper, you don't necessarily feel that way. And there have been kind of plans to try to simplify the theory and to try to understand the physical origin exactly, because it's kind of the way they did it is very non-intuitive. So maybe I will start by saying how you can get to a physical intuition for this local APE theory. And the way to do it is using what I call the universal form of the Navier-Stokes equation. So the key thing is to use static energy, which is a sum of enthalpy plus geopotential. And enthalpy is a function of entropy, salinity, and pressure in the ocean. So you have a pressure derivative gives you the specific volume of the inverse of density. The geopotential derivative is just one. The thermodynamic derivative gives you the in-situ temperature and chemical potential. So you can always write the Navier-Stokes, the momentum equation and the continuity equation in terms of static energy or the derivative of static energy. But what's important when you do that, then you have to realize sigma, or static energy, is a function of 4 variables, independent variables. But the momentum and continuity equation only depends on the pressure and geopotential derivative. That means everything that is thermodynamic function of entropy and salinity doesn't impact the dynamics. So you can use this idea to say that then I can remove, if I'm able to identify something that depends only on entropy and salinity, I can just remove it from static energy, and I can rewrite the dynamics, momentum equation and continuity equation in terms of this, what I call the dynamical complement of static energy. In fact, you realize that there is a big chunk of static energy that is completely invisible to the dynamics. So the key, in order to define available part, you have to specify this big chunk here. And what you do is to define this chunk as a value of static energy in Lorenz reference state of minimum potential energy. So if you do that, so you need a way to compute this Lorenz state of reference potential energy. So it's not really the topic of this talk to show how to do it. There is a paper by Sainz et al. You can compute it in the ocean. It looks very linear. It's relatively smooth and nice. And you can compute, if you know the reference profile, you can compute the reference position of a free parcel in a reference state by solving a simple equation, which means the density of a parcel you move by conserving theta and s that match the density of the environment. You can make plots of, you can compute the reference position in the ocean. So for instance, in the Antarctic, you find that all the parcels in the Antarctic circumpolar current have a reference position about 5 kilometers. That means all these parcels want to go to the bottom of the ocean. On the outside, you find the reference position of parcel is very close to the actual position. So instead is a Antarctic bottom water that is out of equilibrium relative to the Lorenz reference density. You can compute the APE, you find very large amount of APE in the Southern Ocean and very small value elsewhere. So physically, you can write equation defining the Lorenz reference state. Basically, if you have a density surfaces, you just flatten things like that. So the volume of water here is the same as here. So what is important is this, also what I'm going to talk about is not limited to the fully compressible Navier-Stokes equation. It is applicable to all kinds of soundproof approximation. So with Thomas Dubo at LMD, we find a way to write the Navier-Stokes equation as I did. All you can do to preserve exactly the same properties, energy conservation properties as the Navier-Stokes equation, you just approximate the static energy. And the form of the equation doesn't change. You just take it and plug another form of static energy, which you obtain by a Taylor series expansion, where you approximate the pressure by reference pressure. On all your different soundproof approximation are obtained by various degrees of simplification of this. So, for instance, but what's important is that every approximation of static energy is a function of the same variable. So structurally, it doesn't matter. So you can write the equation of motion in a way for which the exact form of static energy, whether it's exact one or approximate one, doesn't matter. All the energy conservation properties are only dependent on static energy being a function of this four variable. So it doesn't matter whether it's approximate or not. So when you do that, you realize that there are some universal form of energy and some non-universal form of energy. So you find that when you do that, you find things like static energy, potential energy that is related to static energy in this way, available potential energy and backup potential energy. So all the form of energy that relates to static energy are universal in some way because you can always define regardless of the approximation or looseness or whatever. But some form of energy, like internal energy or gravitational potential energy, which sounds fundamental. In fact, you cannot deduce them from the form of static energy. So what they mean, looseness fluid becomes ambiguous. So you have, so that's why there have been a lot of confusion in the literature for the gravitational potential energy, the looseness fluid is kind of ill-defined somehow. So you can decide arbitrarily, but there is no fundamental rule to do it correctly. So just on the series and for the form, that means the exact form of the local form of APE depends on the approximation we are making. So here's just a slide that shows you that in the most general case, the local APE density, the difference of static energy between the actual position and the reference position is non-negative. For business fluid, it's just an integral of buoyancy forces defined relative to the Lorenz reference density profile. So you have simple form, it's not quadratic. So it looks maybe complicated from the viewpoint of partitioning into mean or eddy component. But, so I'll come to that. So just now in terms of the differences, so when you use this definition, this approach, so you find that the total APE, if you integrate it over the volume, it's going to be the volume integral of something that is non-negative, which is called the internal form of internal APE, and you have a volume integral of the reference pressure profile. And when you expand it in order, you find that is the integral form, n squared theta squared over 2. And there is this external shallow water APE that's related to the square sea surface elevation variance that we know exists in shallow water model. But if you use a classical approximation, it's very hard to find this term in Lorenz approach. So it's an advantage that you get these terms that you know exist. So to decompose things into mean-to-eddy, that's complicated and has been a source of trouble because you have a quantity that is non-quadratic, and how do you decompose a non-quadratic expression into mean-to-eddy complement? So in fact, it's really simple. So what happens is the APE density is often convex function. For convex function, you can just linearize around some mean value. And you know that if you remove the linear part for a convex function, the residual is going to be positive. So all you have to do to have a mean-eddy decomposition, you take your simple fluid, simple business fluid, AP density is a function of density on Z. Then you define the mean as a density, the AP density of the mean density. That is the first term, and with the average, you define the ADAP as a convex part of your AP. You can do that for the theoretical approximation. You define the mean AP as the AP of the mean comparison stability, and you are left with a residual. So now in terms of the differences, again, I carry on with the differences. So one thing that's important is the mean-to-eddy conversion. So here I'm just for illustration, I assume the turbulent density flux is controlled by the turbulent density flux. And here, just to illustrate, I assume there is a down gradient closure for the density flux. I need to introduce the slope vector, which is kind of a standard quantity in a mesoscale parametrization. And there is a lambda factor that this is the ratio of the local mean buoyancy frequency squared over that of the Lorenz reference state. And you find that for the exact mean-to-eddy conversion, you get something like that, and this is proportional to K-rho times the mean n squared. And this is a QG approximation. So the QG approximation for down gradient closure is always positive. That means in the Lorenz, in the QG approximation of the LEC, you always find a mean-to-eddy conversion. There is only one way for the conversion to happen. And it corresponds to, this case corresponds to lambda approximately equals to 1. But in the general case, where lambda it can be significantly different from 1, then it's possible to have a negative value. That means in an exact Lorenz energy cycle, we can in principle have a backscatter of energy from ADAP to mean AP. And that is invisible in the classical approximation. So it's interesting because we know that from themselves that backscatter should exist in reality, but it's always maybe from numerical simulation. So here you have a simple justification for it. So it means in a model, in principle, you can have a diffusive instability or weak mixing, and in principle, destabilize your fluid. So if I look at the ADAP budget, what's interesting is that the exact, so that means now I'm focusing on this reservoir. And so there are two main conversions that fill the reservoir. So what's interesting with the exact ADAP budget is that it only involves the diagonal component of the density field. But if you take the approximate, it's much more complicated form. And it has to balance the AP distillation, the mixing. So it means in the exact formula, you get a constraint on what are the right density surfaces in the ocean. And you don't see this information in the approximate version. That's interesting that the idea that the ADAP, exact ADAP constrains the direction of lateral mixing of the density surfaces in the ocean can be tested. So what it predicts is that the density surfaces, the right density surfaces in the ocean should be defined in terms of the Lorenz reference density surfaces. And here is the comparison, but oceanographers have convinced themselves that it should be the neutral surfaces. So there have been but when I compare the two, so I compare the neutral density surfaces with gamma T, this my surfaces. So gamma N surfaces is the red dots, and the gamma T is the black solid line. So you see that you cannot distinguish between the two surfaces, and they have often completely different arguments. Neutral surfaces, you look for neutral paths that minimize the effect of buoyancy forces. The Lorenz reference density surfaces are just the surfaces that are flat. in a state of rest. And you can see that they only differ in the Antarctic, in the cold water, because you start to have some differences. So in this paper, I argue that if you mix along the neutral direction, in fact, they are not the right direction to mix along, and you get spurious mixing basis. One point, when you compute the AP generation, so the AP generation depends on the surface buoyancy fluxes in the standard approximation. In the exact theory, you get something that looks similar as the buoyancy fluxes, but you get a vertically average value of thermal expansion and ion contraction coefficient. And the coefficient in front of it is different. Here it's always negative, while in the Lorenz approximation it can be positive or negative. So the problem with this the Lorenz approximation, you can get large positive AP generation in the equatorial regions. In the exact theory, you can only get positive AP production when the buoyancy fluxes are destabilizing the water column. So it's while in the Lorenz approximation, you can get large AP production where you stabilize the water column, which is less physically intuitive. So here's a plot from Jin Song paper, it's quite famous and highly cited, where you find the peak of AP production in the Lorenz approximation in the equatorial region. But in the exact theory, you find in the equatorial region a small negative number. And in the exact theory, you can only find significant AP production at high latitude when you destabilize the water. But finally, two slides to illustrate this slide to kind of compare how the approximation performs on the mean AP. So here is just a cross section between the Atlas and Antarctica. And I find that for the mean AP, it's hard to find any significant difference between the two approaches, which is good. So here is the ADAP, so it's a decimal logarithm. This is the exact ADAP. And this is Lorenz approximation. This is eddy kinetic energy and the mean kinetic energy. So you can see that the ADAP is slightly more intense in the exact than in the approximate version. I was trying to find a correlation between the ADAP and the eddy kinetic energy. So it's not really striking, but it's there, but it's not obvious. So to summarize, so I've used the exact local AP theory to assess the validity and accuracy of this Lorenz approximation that has been underlying the majority of LEC studies. So I think the conclusion is that in French from the Lorenz approximation can be completely wrong and unphysical for some aspect like the AP production to slightly inaccurate. But even where it is inaccurate, the exact theory gives you more information about the physics of the system than the Lorenz approximation. Like for the ADAP budget, the exact version tells you what are the right definition of density surfaces, but the Lorenz approximation doesn't tell you anything specific. And for the mean to AP conversions, another important thing is that often it's very close, you cannot see the difference. But in places where you have a strong slope, like maybe a Gulf Stream or in the SEC, you can occasionally, in principle, backscatter mean AP into ADAP, which does not exist in the Lorenz approximation. So it means that if you are precisely these energetic regions like the Gulf Stream or SEC are the regions that really you want to understand because there is a lot of turbulence on mesoscale generation. So this is an advantage. It would be good to re-examine studies in these regions where we expect differences between the two frameworks. And the final point is that this local AP theory doesn't really look at potential energy, but static energy. It says that it's really the static energy that is the dominant quantity. So that means you minimize everything is in terms of potential energy is less important in the theory. So it gives the same result more or less, but things are easier to understand when you use static energy. That's it.